So the first problem that we're gonna look at today is an MDP, and we want to do policy iteration. But first we'll start with writing down the transition function and the reward function for this MDP. Now, so in this problem, it's similar to the discussion section last week, where we play a Micro-Blackjack game, and you repeatedly draw a card that can be 2, 3, or 4. Now, you can take two actions, either keep drawing or you decide to stop. And if your total score is less than 6, then you get that for, and then you decide to stop, then you get that for your reward. Now, if your score is at least 6, you would end the game and you receive 0 utility. Okay, so let's first write down the transition function for this MDP. So I'm gonna write down non-zero transition first. So if I'm at state S and I take action stop, I will probably I'll always end up at state done. So that means that I have probability 1 of ending up at state done. Now, if I decide to draw, I'm gonna break it down into 5 or 6 different states. Either I'm at state 0, 2, 3, 4, 5, or done right now. So first, if I'm at state 0 and I decide to draw, that means that I could end up at state 2, 3, or 4. So I'm gonna have 1/3 chance of ending up at state 2, 3, and 4. Now, if I'm at state 2 and I draw, I would end up at 4, 5, or 6, and 6 means done. So I'm gonna get 1/3 probability for S prime in 4, 5, and done. All right, so now if I'm at state 3 and I draw, this time if I draw either 4 or 3, I would end up at done. So I'm gonna get 1/3 only when S prime is 3, or only when S prime is 5, and otherwise I would get 2/3 for the done state. Now, if I'm at state 4 and I draw, I would always end up with something greater than or equals to 6. So I'm gonna always get done no matter what I draw. And it's the same for 5 and the same for done state. Oh, actually for done state I cannot even draw, so I'm gonna even ignore this. So you can say that this is 1, or you can ignore it. And okay, so otherwise I would so if I'm not in one of these, if I'm not in one of these situations, I would always get 0 probability. Okay, so now let's look at the reward function. So let me erase this. Okay, so the reward function. So when do we get non-zero reward? So let's say if I it's only when I decide to stop. So I'm gonna say that this one, if I take action stop, then I would get something non-zero, and I would actually get S if S is less than or equals to 5, and otherwise I will get 0 reward. So that concludes our first subproblem. Okay. So now let's look at policy iteration. And in policy iteration, we alternate between policy evaluation and policy improvement. And in this problem, we'll do one iteration, which, given the current policy, we want to evaluate the expected total expected return from each of the 5 states, and that's our V function. And after we get the V function, then we'll do policy improvement, which means we want to find the best policy according to the evaluation function that we estimated. So now let's do the let's first do the policy evaluation. So given the current policy, we'll write down Bellman equations for this. So let's say at state 0, and I applied this policy pi I. So I would decide to draw. So I would end up at either state 2, 3, or 4 with the equal probability. So I have the probability 1/3 of arriving at state 2 plus probability 1/3 of arriving at state 3 plus probability 1/3 of arriving at state 4. And notice that I don't get any reward after I decide to draw, and I only get that when I decide to stop. So now if I'm at state 2, I can compute my Bellman equation this way because I decide to stop. So I get 2, and the game terminates. Now if I'm at state 3 and I decide to draw, I would end up at 5 or done, right? So if I end up at 5 with probability 1/3, and this means that I get the evaluation from state 5 for my total reward, and with probability 2/3, I'll be at state done, and I get 0 for my reward. Okay, so now 2 more. So if I'm at state 4 and I stop, I definitely get 4, and that's it. If I'm at state 5 and I decide to draw, So I would always get 0 because I'm gonna be done and I'm gonna be out of bound basically. So I'm gonna fill this in the value that I know. So I know 4, I know 2. Okay, so to get V3, it's gonna be 1/3 of Vi5, which is 0. So we're gonna get 0 for 3. And for V0, we'll get 1/3 of the sum of 2, 3, and 4. So that would be 2. Right? So now, given this value function that we approximated from pi I, we want to get an improvement for pi I plus 1. And in order to do that, we'll get our pi I plus 1 will be the maximum action and of the reward that you would get. Well, let's see. You sum over all the possible next states, and in the value from pi I, and we have discounting factor gamma here, and then we have the transition function, which is SA and S prime, right? So you can end up at like state one of the states, and we call that S prime, and from S prime, sorry, this would be S prime, and from S prime we get the future reward V of S prime, and the current reward R of SA and S prime. So and then we can get the best action for our pi I plus 1. Okay, so this is a policy improvement, and let's start from 5. So we're gonna have pi I plus 1. You can apply this from state 5, and there are 2 different actions that you can take. So let's consider draw first. So if I draw, what would I get? So actually, yeah, let's break it down like, okay, is 5, so 2 actions. If I draw, then I can evaluate this. Well, I'm gonna always end up at done, and I'm gonna get 0 reward. So if I draw, I would get 0. But if I stop, I would get the reward right away, and that's 5. Okay. Now, if I, so this one, that means that if I stop, I would get a much higher reward. So I'll always decide to stop. Now, if I'm at state 4 and I decide to draw, again, I'm gonna be out of bound and I'm gonna get 0 for sure. But if I decide to stop, I'll get 4. Sorry. So that means that stop is a better option for me, given the current value function. Okay, so now if we at state 3, again, if we draw, then we would either end up at 5 or done. and we would end up at 5 with probability 1/3, and that's the t here. And then we'll get, well, the reward from this draw action is 0, but we'll get the value function from state 5 here, which is v of 5, and v of 5 is 0. So if I draw, I would still get 0, but if I stop, I would get 3 right away. So that means that stop is still a better option for me when I'm at state 3. Now let's look at state 2. Okay, so when I draw, I might end up at 4, 5, or done. And if I'm at state 4, then I would get, well, I would get 0 reward from the current draw action, but I'll get 4 from my value function at state 4. If I draw 3 and I'll end up at 5, I'll get 0 for the draw action, but I'll also get 0 at state 5, so that's gonna be all 0. And if I draw 4, and I'll be 6, and that's done, and then I'll get 0. Yeah. So this total gonna be 4/3. Whereas if I stop, I'll get 2. So that means that 2 is still a better option than 4/3, right? So I'm gonna stop here. Okay, so the last one is when we at state 0. So I can either draw or stop. So if I stop, I'll get 0. So hopefully this time draw would give me a better reward. So I could end up at 2, 3, or 4, and with probably 1/3 for each. So if I end up at state 2, I'll get 2 for my approximated sum of reward. If I get to 3, then I'll get probably still get 0. But if I end up at state 4, then I'll get yes, I'll get 4. This should be 0 if I stop. Okay, so now my Q function approximation for this draw action would be 2. So you can see that 2 is better than 0. So if I draw, then I'll get a better result, and that concludes one iteration of policy iteration. Okay, now let's move on to problem 2, which is TD learning and Q learning. In this MDP, we'll have an agent running, and there are 5 different states, A, B, C, D, E. The agent can move east, south, west, north, and we let it run, and we observe some transitions that contain state, action, next state, and reward. So we observe these 4 transitions. Now we want to learn value function and value. Well, from TD learning, you get state value function. From Q learning, you would want to learn state action value function. Let's see how can we compute the updates after we have seen 4 observations. And here we have gamma, which is a discounting factor of 1, and we have the alpha, which is the hyperparameter for the learning rate, 0.5. Okay, so first, what is TD learning? So in TD learning, you let's say you observe a transition is A is prime, and then you get reward R. And your current value function is V pi, and you want to update your V pi S by think of alpha something small that less than 1. So you would maintain the value function from the previous round, and you with some small updates alpha, you would want to use the current transition. And the current transition, well, that's like one step look ahead, which means that after you take this action, you estimate the total reward using this action, and the reward that you get right away after you take this action is R. Now you would have some discounting factor gamma, and the expected future reward would be the value function from the previous iteration. So you'd get this update, right? So in this case, after we have seen B is C2, well, initially everything is 0, but after we have seen B is C2, our VB would be 0.5 times S, sorry, it should be S prime, and it should be 0.5 times the current V pi B, and that's 0, plus 0.5 times V pi, it's gonna be 2, the reward that we have right now, times 1 times V pi at S prime, and S prime is gonna be C, and this is also 0 right now, so we'll get 1 for VB. Similarly, we make the update, the next update, C south E4, so 0.5 times V pi C currently, which is 0, and then 0.5 times the reward right now is 4, and the future reward would be V pi E, because we end up at E, and this is also 0, so we get 2 for V pi C. Okay, so here we're gonna update C again. So we see E is A6, and we have the current V pi C, which is 2, and 0.5 times current reward is 6, and future reward from state A is gonna be 0, and here we'll get 4. Okay, so now the last one, after we have seen VB is C2, we're gonna update VB, and we're gonna update it by 0.5 times the original VB, which we had from previously 1, plus 0.5 times the reward right now is 2, and gamma is 1, V pi of C, oops, sorry, okay, so V pi of C, let me erase this, V pi of C, which gonna be 4 from previous iteration here, and in total we're gonna have 3.5. Okay, so after we have seen the 4 observations, we're gonna end up with VC equals 4, VB equals 3.5, and everything else is gonna be 0. Okay, that's for TD learning. Now let's do Q learning. So in this case, instead of using only action value function, we're gonna have instead of using only state value function, we're gonna have action as well, and that means that if we have, let's say, observe this transition as A, as prime, and R, then we would update Q pi at S and A by a factor of 1 minus alpha of the previous value function and factor of alpha of the reward that we just get right now, and the best possible action that we would get. Notice that this is A prime because it's gonna be the best action from state S prime given that we arrived at state S prime. So for this problem, we first gonna have, let me write here, so I'm gonna have B is C2, C south E4, C is A6, and B is C2. Okay, so that we can see it here. All right, so the first one, we're gonna update Q pi from state B, taking action is, right? So originally everything is again 0, and this one would mean that we're gonna have 0.5 of the previous one, which is 0, and 0.5 times the reward 2 that we just get, and the best action that we can take from C, which currently is still 0, and that means we get 1. Now if we at state C and we take action south, we're gonna have 0.5 times the Q function, the current Q function from C is taking action south, which is still 0, and 0.5 times the reward that we just get, 4, plus the Q function from E. What the best action that you can take from E is still 0, because we haven't updated anything about E, and that means that we're gonna end up at state 2. Now we're gonna update C east, and notice that it's not gonna replace C south because they have different actions. So from C east, again we still have 0 because we haven't visited this exact state and action yet, and the reward we get is 6. So it's gonna be 6 plus whatever the base action you can take from A, and since we haven't visited A, this is gonna be 0 still, and we're gonna get 3. And finally, from state B and we take action is, now this gonna override what we had before, and now we have 0.5 times 1, which is from previous iteration, and 0.5 times, we end up at state C, right? So it's gonna be the best action that you can take from C. First you get reward 2, and then the best action you can take from C is from our Q function is gonna be east, and that's 3. So we're gonna get 3 here, and as a result we get 3 for Q pi b east, and that concludes our Q learning updates. So we get QC south 2, QC east 3, QB east 3, everything else is 0. Alright, so sometimes when we apply Q learning and we have a very large state space and action space, it is difficult to apply Q learning, tabular Q learning directly. So in this problem, we'll look at how can we write down some features, just like the heuristic, and then use that to evaluate our Q function, and it would cluster different states and actions together, and that would significantly reduce the search space and the parameter space for our problem. And in this problem, we'll have a Pacman and ghosts and food pellets. So and then we in the first problem, let's say we have 2 features. One is the number of ghosts within one step of the Pacman, and the second is the number of food pellets within one step of Pacman. So what is these 2 features in this figure here? Is gonna be the number of ghosts is gonna be 2, and the number of food pallet is gonna be just 1. Okay, so pretty straightforward right now. And then the second problem, we'll try to evaluate our Q function at the particular state that we had above, and that's gonna be, so my Q function at S and A is gonna be some weight WG times FG at the current state and action, and WP the weight. So this is like linear right now, and we're gonna have FP at state S and A. So from what we had above, and the weight 100 and minus 10, we can compute the Q function as follows, and this would give you 190. Okay, so this is a Q function of the state above given this weight. Now let's okay, so let's compute the sample estimate of Q function. So Q, right? So now I am at state S, I take action A, I end up at state S prime and get reward R, and I know that my feature become 0 and 2, and the reward I got is 50 with discounting factor 0.5. Okay, so first let's write out the formula. So, well, first you would get the reward R from this sample, and you can calculate future reward from this estimated. Okay, so it's gonna be max over A prime, and Q is prime A prime, just like the problem we had before. And we know that our reward is 50, our gamma is 0.5, and the base action, well, because Q function doesn't depend on the action right now, it only depends on the states. So that means that I can directly roll all the Q function from S prime A prime is gonna be just a Q function. It's gonna only depends on S prime, and that's gonna only depends on FG and FP. So I can estimate this whole thing by just W of FG, WG is FG plus WP FP of the current, of the next state. No, because it doesn't depend on A prime again. So and then this I'm gonna write it down here. So what do we have for WG? It's gonna be 100 times FG, which is 0, plus minus 10, which is the weight for FP, or for the FP, and FP is gonna be 2. So we're gonna have this sum is gonna be 50 minus 10, and it's gonna be 40. Okay, so now in problem 4, we will compute the update for WG and WP. So for WP, we gonna keep the previous estimation, and we gonna have some learning rate alpha and times the gradient of WG, and from the class we know that this gonna be the difference between the sample estimate Q and the current Q function that we had. So and then we're gonna have F of G SA. So let's compute this. WG, previously we have 100, and the weight is 0.5, and this sample estimate we had from previous problem is 40, and the current Q estimate is 190, and FG has become 0. FG from the previous iteration, which is 2. Now, so this would become minus 75 times 2. This would be 150, and this would be 100, and we get minus 50. Now for WP, you have the previous WP plus the learning rate times the difference between the sample estimate of Q and the current estimate of Q times the the feature of the food pallets, and that was 1. So we're gonna have minus 10 plus 0.5 times the sample estimate of Q, which was 40, minus 190 times 1, and that's gonna be minus 75 and minus 10, so we're gonna get minus 85. So this concludes our new update for with WG and WP. Thank you.